This is my APFRQ video project. For my project, I'll be doing 2010 FRQ number 6. This problem states that solutions to the differential equation dy over dx equals xy cubed also satisfy d squared y over dx squared equals y cubed times 1 plus 3x squared y squared. And it says let y equals f of x be a particular solution to the differential equation dy over dx equals xy cubed with f of 1 is equal to 2. Part A states, write an equation for the line tangent to the graph of y equals f of x at x equals 1. So from the original question, we know that f of 1 is equal to 2, so y equals 2 and x equals 1. So now if we evaluate dy over dx at 1, 2, it gives us the slope of the tangent line at x equals 1, which is equal to 8. So using point slope formula, using the point 1, 2, we arrive at y minus 2 equals 8 times x minus 1, which is the equation of the tangent line at x equals 1. Part A is worth 2 points, and the scoring rubric is quite simple. So if you find f prime of 1 correctly, which is the slope of the tangent line at x equals 1, then you get 1 point. And for finding the correct tangent line equation, you get the second point. So as long as you do both those correctly, you get full points on Part A. Part B asks, use the tangent line equation from Part A to approximate f of 1.1. Given that f of x is larger than 0 for x is larger than 1 and less than 1.1, is the approximation for f of 1.1 greater than or less than f of 1.1? Explain your reasoning. So by plugging x equals 1.1 into the equation obtained from Part A, we get y equals 2 plus 8 times 1.1 minus 1, which is 2.8. And this is the approximate slope of the tangent line at x equals 1.1. We are given that y equals f of x is positive on the interval x is larger than 1 and less than 1.1. And from this information we can infer that all x and y values are positive on the interval. And here we can see that the second derivative, or d squared y over dx squared, is equal to y cubed times 1 plus 3x squared y squared. And because both x and y are always positive on the interval, we can infer that the second derivative is always positive on the interval, because the inside will always be positive because there's x squared and y squared, and y is always positive, so y cubed will always be positive. So because the second derivative is positive, this means that f of x is concave up on the interval. And when you have a graph that's concave up, that means the tangent line always lies below the graph, which means that the approximation for f of 1.1 is less than f of 1.1. And this trick for seeing if the derivatives or the second derivatives are positive based on just the x and y values being positive is a great way to save time on an AP test. Part B is also worth 2 points. So you get 1 point for finding the correct tangent line approximation, and then the second point you get for coming to the correct conclusion about what this means and giving an explanation for this. Finally, Part C asks, find the particular solution y equals f of x with initial condition f of 1 is equal to 2. So using the differential equation dy over dx is equal to xy cubed, we can separate the variables, giving us 1 over y cubed dy is equal to x dx. And by taking the integral of both sides, we obtain negative 1 over 2y squared is equal to x squared over 2 plus c. And you might notice that there's only a plus c on one side of the equation. And that's because if there's a plus c on both sides of the equation, we could move one c on the other side, giving us c minus c, or a constant minus a constant. And a constant minus a constant is just another constant. So this allows us to represent c on only one side of the equation. So now we can solve for c. And by plugging in the initial condition f of 1 is equal to 2, we get negative 1 over 8 is equal to 1 over 2 plus c. And c is equal to negative 1 over 2 minus 1 over 8, which is negative 5 over 8. So now, by plugging c back into the equation, we get negative 1 over 2y squared is equal to x squared over 2 minus 5 over 8. And by finding a common denominator for the right side of the equation, we get negative 1 over 2y squared is equal to 4x squared minus 5 over 8. And now by taking the reciprocal of both sides and dividing the top by 2, we get y squared is equal to 4 over 5 minus 4x squared. And now, by taking the square root of both sides, we get y, or f of x, is equal to 2 over the square root of 5 minus 4x squared. And you might notice that there's no plus or minus in front of the 2 over a square root of 5 minus 4x squared. And that's because the initial condition f of 1 is equal to 2 is positive, which means we only take the positive instead of both the plus and the minus. And there's also a domain for this, which is x is larger than negative root 5 over 2 and less than root 5 over 2. And this is to ensure that there's no negatives in the square root on the bottom or zeros in the denominator. Part C is where the majority of the points for this FRQ come in. And it's worth 5 points. So you get 1 point for separation of variables, just putting the y dy and then the x dx on each side. 1 point for antiderivatives, just taking the antiderivatives of the functions correctly. 1 point for constant integration, so just remember to add c. 1 point for using the initial condition, so just plug the initial condition given into the equation to solve for c. And then 1 point for solving for y correctly. And the thing to note is that if you do not separate the variables, it makes the rest of the question incorrect and you get 0 out of 5 on the FRQ. This part of the FRQ. And if you do the separation of variables and the antiderivatives correctly, but you forget the constant of integration, then you also lose the points for using the initial condition and solving for y, giving you 2 out of 5 on the FRQ Part C. This concludes my explanation for 2010 FRQ number 6. And if you're looking for additional practice for these types of questions, I compiled some FRQs which are similar to this question. So here are some practice for finding particular solutions for differential equations and also for finding tangent lines and approximating them. Thanks for watching.